Today we'll look at charge density functions, which describe continuous charge distributions in a body. So basically the charge density rho gives the volumetric charge density. So that will be in coulombs per unit length cubed. And using Gauss's law, we can determine a function that describes the electric field as a function of the radial distance from the center of the body. So we'll start off by looking at where the radius is less than or equal to the radius of the body. And the radius of the body is the radius of this spherical body. So to determine the variation in electric field inside that body, so we take a spherical surface inside that body, which is a radial distance of r from the center. And using Gauss's law, the electric flux is going to be the electric field multiplied by the surface area of that interior surface. So that would be 4 pi r squared. And that's equal to the charge enclosed in that surface over the permittivity of free space. So now the enclosed charge in that surface can be determined using integration. So if we multiply the charge density function, which is rho m by r on the radius of the body, and we multiply that by the differential volume element and integrate that from 0 to r, which gives the charge enclosed within that interior surface over here, which is spherical. An expression for the differential volume element in terms of the radial distance from the center of the charge can be obtained by dividing this surface into infinitesimally thin spheres. And these thin spheres are going to have an infinitesimal thickness dr. So if you can imagine, the surface area of one of these spheres is 4 pi r squared, and then multiplied by the infinitesimal thickness of the sphere, and then multiplying by rho m by r on r, and integrating from 0 to r, gives us the total charge enclosed within that green surface. So if we take the constants outside the integral, we get 4 pi rho m on r, and we integrate r cubed over r from 0 to r. So that gives us 4 pi rho m on r, and that's multiplied by r to the 4 on 4, which is equal to pi rho m on r by r to the 4. And now we can substitute this into this equation. So the charge enclosed is pi rho m on r by r to the 4, and we divide by the permittivity of free space. So we can cancel out pi, and we can cancel out r squared. And therefore the electric field is going to be equal to rho m on 4r epsilon naught by r squared. So it varies parabolically from 0 to r, and if we substitute for r into this expression, we get rho m by r squared on r, which is r, over 4 epsilon naught. Now to get the electric field for r greater than r, well, we can also use the electric flux. So this time we have the electric flux multiplied by the surface area of a surface constructed outside the sphere, which has a radial distance of r from the center, and that's equal to the charge enclosed. So this time the charge enclosed is in that entire sphere. So we instead integrate from 0 to r, and that's going to give us pi rho m on r by r to the 4, which is equal to pi rho m r cubed. And if we're substituting for the enclosed charge in the flux equation, so pi rho m by r cubed, and we divide by the permittivity of free space, and if we divide by 4 pi r squared, so pi cancels, and we get 4 in a denominator and r squared in a denominator. So the electric field is inversely proportional to the square of the radius from the center of the charge for r greater than or equal to r. So it's going to vary as follows. And if we substitute for capital R, well, what we get is rho m by r on 4 epsilon naught at r. And I'll see you in the next video.